Welcome to The Explainer. Today, we're going on a trip, a really fascinating spatial journey, actually. We are going to travel all the way from the boundless, virtually infinite realm of the centralized cloud, down through the intermediary network layers, until we reach the microscopic field sensors interfacing directly with the physical world. Understanding this journey, well, it's absolutely crucial because it's the key to the future of automation.
So how do you classify edge hardware platforms and evaluate their trade-offs under architectural constraints? If you've ever stared down a brutal network engineering university exam paper, you have probably seen a question exactly like this one. It's a classic for sure. And to completely master this topic and essentially unlock the cheat code to answering it, you need to understand that the secret lies in one very specific foundational engineering framework.
Here is our syllabus for today. First up, we'll hit the SWaP-C framework. Then we'll walk through Tier 1 micro-data centers, Tier 2 edge servers, and Tier 3 resource-constrained devices before we bring it all together by synthesizing a complete hardware taxonomy.
Okay, let's dive into this. Part 1, the SWaP-C framework and its core hardware constraints.
To accurately classify any edge hardware, you literally must view it through the lens of SWaP-C. That stands for size, weight, power, and cost. You see, as computing moves out of pristine, climate-controlled server farms and gets closer to physical actions in the real world, these four parameters become an intense pressure cooker. Every single design choice made by hardware engineers is a delicate balancing act of these exact constraints.
It's a pretty stark contrast. Up at the centralized cloud tier, SWaP-C is virtually unconstrained. You have multi-megawatt facilities, infinite physical space, and massive dedicated liquid cooling loops. It's a pampered, air-conditioned life for a server. But the physical edge? The edge is rugged. You are dealing with dramatically tightening hardware constraints and harsh, unpredictable environments. You simply cannot drop a standard cloud server into the muddy, rugged reality of a farm field or a dusty factory and expect it to survive.
Which brings us to Part 2, Tier 1, Micro-Data Centers are regional edge hubs.
To really understand a micro-data center, just picture a modular deployment, something like AWS Outposts or a Schneider Electric EcoStruxure pod, sitting right at the base of a 5G cellular tower. In the real world, this roadside hub aggregates live data feeds from hundreds of connected, autonomous vehicles across a 5-kilometer radius. It's running massive, localized deep learning inference models to coordinate intersection traffic safety in real time, completely bypassing the need to wait for a sluggish response from some distant cloud. Now, what's really interesting about this setup is the sheer density. These are basically fractional hyperscale data centers. We're talking 1 to 10 server racks packed with high-end Intel Xeon or AMD EPYC processors, boasting 100 to 400 gigabits per second of fiber backhaul. They can host thousands of virtual machines concurrently. And because they operate outdoors, they're entirely self-contained, featuring integrated UPS systems, fire suppression, physical security locks, and totally autonomous climate control. They essentially bring the immense power of the cloud right into the elements.
Let's step a bit deeper into the network. Part 3. Tier 2, Edge Servers on the local facility floor. Edge servers are your industrial-grade computing appliances. Imagine walking into a modern, automated, friction-free retail checkout store. You've got overhead smart cameras constantly capturing shoppers pulling items off shelves. Now, if you tried streaming 20 separate 4K video feeds over the open internet to a cloud data center, you would waste immense network bandwidth and introduce totally unacceptable lag. Instead, an edge server processes those heavy computer vision models locally, right there in a dusty retail backroom.
Processing on-site like that yields blazing fast execution speeds. By decoding the video streams frame by frame and running object detection locally, the server can update the customer's virtual shopping cart in less than 10 milliseconds. Only the final, tiny text ledger of the transaction is actually synced back to the cloud. It's incredibly efficient.
To achieve this, the hardware has to be highly specialized. We're looking at compact 1U or 2U rugged chassis, often featuring fanless designs with industrial dustproof seals and cooling fins. Inside, they run high-core count ARM64 processors like Ampere Ultra or mid-tier x86 chips. But the real magic is the crucial integration of AI accelerators like NVIDIA Tensor Core GPUs or Google Coral TPUs, drawing anywhere from 100 to 500 watts of power to crunch those models.
Zooming all the way out now. Part 4. Tier 3 resource-constrained devices at the outermost boundaries.
This tier interfaces directly with the physical world. Picture a smart agriculture deployment.
You have hundreds of tiny soil moisture sensors distributed across thousands of acres of remote farmland. These endpoints don't have access to the electrical grid. They rely entirely on small AA batteries paired with miniature solar cells, and they are expected to survive out there in the dirt for years without maintenance. After all, you can't exactly pay a technician to walk around changing 10,000 AA batteries every week.
Because of these harsh limits, operations must be strictly managed, almost like a really tight financial energy budget. This constraint profile operates like a strict mathematical equation. E total must be greater than or equal to E compute plus E transcription plus E sleep. You have a finite energy capacity in that battery. And in this equation, the absolute most expensive item on the menu is E transcription, the wireless radio transmission. Actually, to put it in perspective, wireless communication consumes orders of magnitude more power, milliwatt for milliwatt, than just processing data locally on the chip.
To survive, the device's lifespan is incredibly brief. Just consider its active cycle timeline. At 0 seconds, the microcontroller wakes up. By second 1, it pulls the analog sensor pins. At second 2, it runs a lightweight algorithm to process the data locally. At second 3, it transmits a minuscule 10-byte packet to a gateway. And then, for the next 15 minutes, it drops back into a deep, ultra-low power sleep. It spends 99% of its life taking a nap just to survive the swap-C constraints.
So the crucial point is, these devices require stripped-down, ultra-low power architectures. You cannot run a standard full Linux distribution here. It would instantly drain the battery. Instead, we use 32-bit single-core microcontrollers like RISC-V or ARM Cortex-M running bare metal C or lightweight real-time operating systems like FreeRTOS. Their memory is restricted to mere kilobytes of SRAM, and they communicate via low-power radios like LoRaWAN, Zigbee, or Bluetooth Low Energy.
Part 5. Let's wrap this up with a comparative synthesis of the hardware taxonomy.
And this brilliantly illustrates the whole picture. If you are preparing for a university exam, this comparative synthesis is your ultimate cheat sheet. Notice the flow here. Network position goes from regional hub down to outermost field endpoints. The CPU shifts from high-density x86 down to single-core microcontrollers. RAM drops from terabytes in MDCs to literal kilobytes in constrained devices. Power plummets from 50 kilowatts per pod down to mere microwatts. The swap-C challenges evolve dynamically as we move outward, from capital expenditure and thermal dissipation all the way to extreme battery longevity and memory constraints at the edge.
Let's move to and see how this builds, because ultimately, this creates a clear macro-to-micro hardware journey. Step 1. Micro-Datacenters bring standard massive cloud capabilities directly to regional or municipal hubs. Step 2. Edge servers act as the localized workhorses for facilities, processing heavy streams right on site. Step 3. Resource-constrained devices operate at the extreme physical edge, prioritizing severe power management over raw computing speed.
Well, we've thoroughly conquered the physical hardware of the edge today, but what happens when we look inside the machines? In our next explainer, we will transition into software architectures and edge virtualization. When you're operating under these tightly constrained swap-C profiles, which approach actually wins the performance battle? Lightweight virtual machines or containers? Think about it, and I will see you in the next explainer to find out.